Occasionally, astronomical events occur on a large scale, billions of kilometers away from Earth, resounding across the universe. Presently, a similar event is approaching. A red giant, even among researchers, is a shocked star arranged at the outer spans of our system. The system is communicating improperly. Signs have been caught all over the universe by the James Webb Space Telescope. Cosmologists have discovered something extremely disruptive. To learn more about this massive heavenly body, Brian Cox, a well-known astrophysicist, gives a grave admonition. A pressing question emerges. Are we wavering on the verge of seeing a catastrophic cosmic explosion that has the power to alter the natural night sky? Before digging into additional details, make sure to subscribe to our channel if you haven't already. The burning question is now waiting. Will this explosion have an impact on Earth? It will be evident from our planet. Stay tuned as we look into the responses to these intriguing questions in this video. Across the vast expanse of the universe, where the heavenly display of birth, life, and death unfolds in entrancing wonder. One specific star has recently drawn the interest and concern of both cosmologists and the general public. This star, Betelgeuse, stands out as a red supergiant in the Orion constellation. It flaunts its immense size and age. Its striking ruddy color and varying brilliance have long intrigued onlookers, but recent events have increased interest in this divine behemoth even more. As we investigate the essence of Betelgeuse, we find ourselves close to the edge of a potentially incredible event in the star's lifespan. But what do these Betelgeuse transformations mean? What does the star's behavior imply? Could this be the start of a remarkable, grandiose display? Betelgeuse, to an unimaginable extent, displays a size approximately 1,000 times greater than our Sun. Its sheer scale makes it one of the stars that exceeds the limits of human imagination. Picture a star so massive that if it were to take the Sun's place, its surface would expand beyond the orbit of Mars, wrapping Mercury, Venus, Earth, and Mars inside its heavenly grasp. This phenomenal size not only highlights the physical monstrosity of Betelgeuse, but also indicates its place in the stellar life cycle. As a red supergiant, Betelgeuse is in the sunset period of its very existence, characterized by expansion and cooling after a lifetime of hydrogen-helium fusion. Betelgeuse is the subject of fundamental questions. Despite being relatively young in cosmic terms, its age in human terms is estimated at around 8.5 million years, quite recent in relation to stellar life expectancies. Its current status as a red supergiant reflects the result of millions of years of stellar evolution, marked by significant transformations, from a bright blue star to the great red giant we observe today. The journey of stars like Betelgeuse unfolds as a constant transformation, driven by the relentless forces of nuclear fusion and gravity. One prominent feature of Betelgeuse's striking red phase is its hue. This dark red color arises from its significantly lower surface temperature compared to stars like our Sun. While our Sun shines at about 5,500 Kelvin, Betelgeuse's surface is cooler, around 3,500 Kelvin. This lower temperature allows Betelgeuse to emit light with reddish hues. But this color is more than just a visual characteristic. It sheds light on the physical condition of the star and the ongoing processes across its vast gaseous domain. Betelgeuse's unusually rich color history boosts interest. Ancient works from Roman sources and Chinese records suggest that nearly 1,000 years ago, Betelgeuse appeared yellow. Only after the 9th century did Arabic researchers describe it as red. This historical color shift is not just an astronomical footnote, but acts as a guide in the star's transformative journey. The fluctuating brightness of Betelgeuse adds another layer of intrigue. It is a semi-regular variable star, meaning its luminosity undergoes periodic variations. This dance of brightness has captivated astronomers and stargazers for centuries. Betelgeuse typically follows a 420-day cycle alongside a longer 5-year cycle, noted as far back as 1836 by Sir John Herschel, and perhaps even earlier in native oral traditions. But what truly sets Betelgeuse apart isn't just its shifting brightness, it's the irregularity. Unlike many stars that follow predictable patterns, Betelgeuse occasionally departs from its usual rhythm, changing unpredictably from dim to bright. This irregularity points to complex and less understood processes unfolding within its massive structure. This has recently become important. Astronomers and stargazers globally have been captivated by a surprising and dramatic change now widely known as the Great Dimming. Everything started in late 2019, when Betelgeuse, the red supergiant shining brightly in the night sky and a notable part of the Orion constellation, began to dim mysteriously. The dimming was so striking that it lost luminosity at an average rate of 0.01 magnitudes per day, reaching its lowest brightness by February 2020. Normally visible to the naked eye even amidst light pollution, Betelgeuse essentially faded. Even amateur observers couldn't miss it. However, there's a critical challenge in tracking Betelgeuse's activities. When we observe a star like Betelgeuse, we are not seeing its current state, but rather its past, due to the amount of time it takes for light to reach us. Betelgeuse is approximately 725 light-years away, which means the light we see today left the star nearly 7 centuries ago. This time delay complicates efforts to predict and track sudden changes in a star's behavior. In essence, we are watching events that took place a long time ago. Betelgeuse's dimming serves as a stark reminder of the complexities inherent in cosmic observations and the limitations of our comprehension when dealing with the immense scales of the universe and the mystery of time they involve. The star's captivating journey and astronomical performance were carefully monitored by Andrea Dupree, the director of the Center for Astrophysics at Harvard and the Smithsonian. Along with her team, she used the Hubble Space Telescope to begin a 3-year study monitoring Betelgeuse's outer environment. These observations enabled an unparalleled understanding of how a variable star like Betelgeuse behaves, with its frequent expansions and contractions leading to fluctuations in brightness. Hubble's sensitivity to ultraviolet light allowed researchers to investigate the star's turbulent outer layers, partially heated by convection cells. Furthermore, a detailed examination of Hubble spectra from various times in 2019 and 2020 enabled measurement of material movement within Betelgeuse's outer environment. The study specifically focused on the magnesium-2 lines in the spectra, which provide information about the star's atmospheric conditions. Observations revealed material traveling at approximately 200,000 miles per hour from Betelgeuse's surface into its outer environment. This hot and dense material eventually expanded millions of miles, forming the precursor to the dust cloud responsible for the dimming. Dupree and her team estimated that, during the event, about twice the usual amount of material from Betelgeuse's southern hemisphere was shed. This significant mass loss is especially noteworthy because, like all stars, Betelgeuse continuously sheds mass, but at a much higher rate than our Sun. But the question remains, will Betelgeuse actually explode in our lifetime? Scientists are divided. While Betelgeuse is certainly nearing the end of its life cycle, predicting the precise timing of a supernova is extraordinarily difficult. Some astronomers suggest the star could explode within the next 100,000 years, a blink in cosmic terms, but possibly far beyond a human lifespan. However, the unusual dimming event and increased activity observed in recent years have led some to speculate that the timeline might be much shorter. Could Betelgeuse be on the verge of a monumental end? If Betelgeuse were to go supernova, it would be a spectacular sight, one not seen in the modern age. The explosion would briefly make the star as bright as a full moon, even visible during the day. It would not pose a danger to Earth, as it's too far away for harmful radiation to affect our planet. Still, its appearance would be historic, an awe-inspiring event for scientists, skywatchers, and the general public. This supernova would also offer a rare opportunity to study stellar death in real time. From the collapse of the core to the release of energy and the resulting shockwave, it would serve as a cosmic laboratory, helping astrophysicists understand how elements are forged and spread across galaxies. Such explosions are responsible for creating many of the elements essential for life, including carbon, oxygen, and iron. The legacy of Betelgeuse, already one of the most studied stars in the night sky, would be forever cemented in both science and culture. It would mark not just the end of a star, but the beginning of a deeper understanding of the universe. Until that day comes, astronomers will continue monitoring every fluctuation and pulse from Betelgeuse. Satellites like Hubble, ground-based telescopes, and next-generation instruments, such as the James Webb Space Telescope, will keep watch, searching for signs of an imminent finale. In the meantime, the star remains a fiery titan on the edge of transformation. Whether it explodes tomorrow or in 100,000 years, Betelgeuse reminds us of the incredible forces at play in the cosmos, and the delicate balance of life and death that governs all things among the stars. So, the countdown continues. Will we witness the celestial finale of Betelgeuse? Only time and light traveling across space will tell. Does this dimming event mean anything for Betelgeuse's future? Is it a sign of a coming supernova, or merely a brief moment in the star's vast and complex journey? Various hypotheses have been proposed to shed light on this phenomenon. One theory suggests it marks a stage in the supernova process, gaining momentum due to the prevalent belief that Betelgeuse is close to the end of its lifespan. Another widely accepted hypothesis implicates dust, which may have come from the star itself, blocking our view of Betelgeuse. A third explanation considers changes in the star's photosphere, its apparent surface layer, which may influence its brightness. Comprehensive analysis using diverse observational techniques has contributed to unraveling this mystery. Spectroscopic assessments showed a decrease in Betelgeuse's temperature, indicating a significant dark spot on the star's surface. This theory gained support from observations revealing a temperature drop of at least 170 Kelvin during the dimming period, highlighting notable surface changes. Eventually, the key to understanding this remarkable phenomenon came from the careful gaze into space by the Hubble Space Telescope. Hubble's precise observations revealed that Betelgeuse's dimming was likely caused by an enormous ejection of material, which then heated and coalesced into a dust cloud, blocking a portion of the star's surface. This dust cloud reduced the amount of light reaching us from Betelgeuse. The cloud was attributed to superheated plasma that erupted from a large convection cell on the star's surface and traveled through its scorching atmosphere to the colder outer layers. After cooling, this plasma formed dust particles, resulting in a cloud that blocked light from roughly a quarter of the star's surface. Hubble's ultraviolet light spectroscopic observations, which began in January 2019, played an important role in reconstructing the time frame preceding Betelgeuse's dimming. These observations detected signs of thick, heated material passing through the star's atmosphere in the months before the dimming event. By December 2019, additional ground-based telescopes observed that the star's brightness was decreasing, particularly in its southern hemisphere. Initially, this material appeared brighter than the star's usual luminosity, eventually culminating in the formation of a shadow as it dispersed and cooled. The recommendation was straightforward. The outward flow of material and the resulting shadow were responsible for the sudden dimming of the star. The scale of this ejection is truly astonishing, pushing Betelgeuse into the cosmic spotlight. The star expelled an estimated 400 billion times the mass typically released in a conventional coronal mass ejection. This expelled material was thought to be enough to offset our moon several times over, marking a major event, not just for Betelgeuse, but also for our understanding of stellar mechanics. But what are the implications of such a massive release of material for Betelgeuse and for broader theories of supernovae? Traditional wisdom indicates that red supergiants like Betelgeuse routinely shed mass before reaching the cataclysmic peak of their existence. However, the scale of this release challenges that idea, hinting at a potentially more volatile and unpredictable conclusion for these stars. Could Betelgeuse be gearing up for the big finale, a supernova explosion within the coming hundreds of years? Later research speculated on how such an event could occur, suggesting it may happen sooner than previously expected, perhaps in just a few years. Additionally, the concept of the bow shock adds another crucial layer to the Betelgeuse puzzle. As this massive star moves through space at about 67,000 miles per hour relative to the interstellar medium, it creates a bow shock, similar to the wake formed by a boat's bow. This phenomenon arises from the star's outer layers interacting with dust and gases from other stars, offering a spectacular display of the star's dynamic behavior and its interaction with the cosmic milieu. But what about Betelgeuse's recent behavior? Its surface cooling and diminished density were observed after the ejection event, leaving the star in a disturbed state even years later. Hydrodynamic simulations suggest a link between the star's convective activities, the mass ejection, and the subsequent changes in its modes of oscillation. That continued instability raises questions about the internal processes driving these changes and the potential effects they could have on the star's future. Additionally, the observed mass loss rate of Betelgeuse is greater than that of many other stars, reflecting an intricate interaction of internal forces. Nevertheless, with energy continuously dissipating through heat, shock, and mass ejection, Betelgeuse's rhythm is changing. The nature of this mass loss points to the star's dynamic and somewhat erratic life cycle, prompting astronomers to reconsider their models of stellar evolution. The profound changes in Betelgeuse's behavior continue to spark widespread debate among astronomers, who who are reevaluating their understanding of the final phases of a star's life cycle. While stars like our Sun will end their lives in a relatively calm manner, transforming into white dwarfs, Betelgeuse's enormous size and unique characteristics suggest it might end in a much more violent way. As a supergiant, it has already surpassed the size and mass required to evolve into a white dwarf. Instead, Betelgeuse's inevitable fate seems to lie in a spectacular supernova explosion, a cataclysmic event that will leave behind a remnant core, possibly a neutron star or black hole. The scale of Betelgeuse's mass loss could signal that this transformation may occur sooner than expected. It's thought that red supergiants like Betelgeuse typically shed significant mass in the years preceding a supernova, but the most recent event, known as the Great Dimming, suggests this shedding process could be more turbulent and harder to predict than previously believed. This unpredictability has led to a renewed sense of urgency in studying Betelgeuse, as it may be one of the very few red supergiants that will undergo such an explosive event within a human lifetime. Astronomers will continue to keep a close eye on Betelgeuse, particularly with regard to its mass loss rate, which is higher than that of many other stars. These ongoing observations are crucial in understanding how mass loss contributes to a star's final stages and may even offer new insights into the mechanisms behind supernova explosions themselves. And with this procedure occurring relatively close by, only 725 light-years away, scientists may have an unprecedented opportunity to witness a stellar death firsthand. If and when it eventually explodes, Betelgeuse could become bright enough to be visible during the day, providing a unique and extraordinary spectacle for both amateur stargazers and professional astronomers alike. While scientists are still unsure of the precise timing, this event could potentially change our understanding of stellar evolution and the fate of massive stars. As technology advances, the tools we use to study stars like Betelgeuse will only improve, allowing us to unlock even more of the universe's mysteries. With every new discovery, the celestial realm becomes that much more fascinating. The unfolding drama surrounding Betelgeuse serves as an illustration of how little we fully comprehend the final stages of massive stars. In the broader context of astrophysics, Betelgeuse's evolving story underscores the importance of long-term stellar observation. Rarely do scientists get the opportunity to watch a massive star change in such a dramatic and measurable way within a single human lifetime. These observations, whether from space-based instruments like Hubble or ground-based observatories, are vital in piecing together the timeline of a star's life, and more importantly, its death. The variability of Betelgeuse also opens a window into the behavior of red supergiants as a whole. Traditionally, the end-of-life stages of these stars have been modeled as relatively steady processes, punctuated by a final explosive event. But Betelgeuse suggests something different, that the road to a supernova might be chaotic, marked by intermittent pulses, massive surface eruptions, and unexpected dimming events. This realization has prompted a reevaluation of how we interpret similar changes in other stars and what they may indicate about their evolutionary paths. Moreover, Betelgeuse's proximity makes it a particularly attractive subject for future missions. With next-generation telescopes like the James Webb Space Telescope (JWST), the Vera-C, Rubin Observatory, and the extremely large telescope, YELT, coming online, astronomers will be equipped with more powerful tools to capture fine-grained data on Betelgeuse's atmosphere, surface motions, and mass loss mechanisms. These tools may help confirm whether the star is truly in its final countdown, or if what we're seeing is simply one more episode in its complex, centuries-long evolution. From a public perspective, Betelgeuse's potential to become visible in daylight has also sparked excitement and curiosity. The thought of witnessing a stellar supernova with the naked eye, something not seen since Kepler's supernova in 1604, connects the public to cosmic events in a direct, awe-inspiring way. It serves as a reminder that the universe is not static, and that even the most ancient and familiar stars are subject to change. As Betelgeuse continues to evolve, it becomes a symbol of both mystery and knowledge, a testament to how much we've learned and how much we still have to uncover. Its fluctuations serve as a celestial signal, urging scientists to refine their models and deepen their investigations. Ultimately, Betelgeuse challenges our assumptions about the life cycle of massive stars. It hints that the finale may not always follow the script, and that even well-understood categories like red supergiants may surprise us. Whether Betelgeuse explodes in a decade, a century, or far later, its current behavior is a gift to science, an unfolding case study in real time that could reshape our cosmic understanding.